Hello. So, okay. So, so in uh, last lecture we mentioned uh, the main issue in Math 4545 or mathematical statistics is try to prove something, right? So in applied stats, we just use the formula. So here we wanted to prove. Uh, okay, so let's say so in statistics, the most important distribution is normal distribution. Okay, normal distribution. We say because for some distribution close to normal, we say the binomial distribution will close to normal, and from normal distribution we can produce some other important distribution like t distribution, and f distribution, and chi-square distribution. Yeah. So in applied stats, we just use the formula, or we know by binomial distribution will close to normal. So we do not explain why. So we just use graph with binomial distribution is just like that. Like here, x can be this number, then uh, on both sides just goes down. So okay, so we say those kind of distribution can be approximated by such a distribution, right? So this distribution is a normal distribution. So we just explain this from graph, not from mathematics. Okay. Okay. So now we want to prove mathematically. We wanted to prove this. Okay. And and also in statistics, most important is we call this is sampling distribution. We have this x bar follow this normal distribution, right? Mu and sigma, what radical a. So statistics is about the data. So where did it come from? We say data come from the population. Such a population. So population usually is too huge. We cannot check all populations. So only we can do is just pick some of them. So we just do a survey, like take some of them. So we call it a sample. Take a sample. So from sample we just pick those. So from sample we can find sample mean. So and sample's standard deviation. So we can have the information from sample. So then our purpose is try to estimate the information about the population. So for population, we have population's average, a population's mean, and a population's standard deviation sigma, right? Okay, so how can we do that? We just based on this result with sampling distribution x bar sample mean will follow a normal distribution. So this is actually the foundation in statistics. Okay. Okay. So this result is, so we say x bar is just like first sample x1 plus x2 plus xn divided by n, right? So this is x bar. So this one will follow this normal. Okay. Okay. So let's forget this this denominator n. So let's say this result and this result is same. Like we just check enumerate x1 plus x2 plus xn will close to this normal. N normal distribution mu, the mean is n mu. Just multiply n. So here become a radical n sigma. Okay. So this result in probability and stats we call central limit theorem, CLT. Central limit theorem. So the question now is how to prove, right? Question. Okay. So how can we prove these things follow this normal? Or how can we prove these two things follow the same distribution? Okay. Now let's say, so let's to prove this CLT. So maybe we try check this question. How to prove, like, let's say, how to prove x equal y. So here x and y are two landing variables. So how can we prove these two landing variables follow the same distribution? Or we can say like this: how can we prove distribution A equal distribution B? A equal distribution. These two distributions are the same. So how can we prove these things? So in order to so let's consider this. Let's say so we know from a distribution we can produce let's say from a distribution we can produce some numbers. We can produce like we can find the mean, like find the mu, like sigma square, like this. For any distribution, we can find mu and sigma square. So what is mu? So what is mu? What is mu? What is sigma? So we say mu is defined as this, average for this x. And what is sigma? Now what is sigma square? Is x minus mu square's average. Or we have the formula equal e x square minus x square. We have this result. Okay. So from here we define those things. Define, we say moment. We call this moment. Moment is like let's say we denote the mu k equals this, equal e x k's average. or mean of xk. Okay, so let's say, so from a distribution, we can find those like mu1, mu2. So here mu1 is just a mean, right? Mu0 is 1, so we can determine, we have this mu0, mu1, mu2, mu3, okay, until infinity, right? So from a distribution, we can produce those moments. Okay, so we say one distribution, one distribution just determine those numbers or moments. Then we just say, how about go back? So we can say like from mu0, mu1, mu2, from those numbers, we can determine a unique distribution. Okay. Okay. So from this mu0, mu1, mu2, mu3, from those numbers, we can produce a polynomial. We define this polynomial. Now let's say, suppose like if we say, give me some numbers like 1, 2, -3, 4. From this we can produce this polynomial like let's say like 1x0, like we can say like 1 times x0 just 1 times 2x, so minus 3x squared plus 4x3. Right? So from those numbers, we can produce this polynomial function. And from this polynomial function, we can go back to determine those numbers. Like how can we determine first number? We suppose that we denote this as fx. Okay, equal 1 plus 2x minus 3x squared, like this, plus 4x. So what is the coefficient? We say this 1 is just equal f0, right? f0. What is 2? 2 equal if we use derivative, so derivative, so if 2 is just the derivative, then let the x equal 0. So 2 equal f derivative at 0, right? So what is this? This is coefficient 3. So this equal second derivative. Then take x 0, but we should divide by 2, right? And what is this? What is this 4? So 4 is says 3 derivative. So the derivative then put 0 and divide by. So here actually divided by 6 or 3 factorial. Or here divided by 2, or we just divide by 2 factorial. So from polynomial, we have those relationship, right? Those coefficients can determine a polynomial. Then from the polynomial, we can determine those coefficients, right? Okay. So now we have those numbers like mu0, mu1, mu2, mu3. We have those mu. Then we can define this function. Let's say from mu0, we say from this mu0 actually is 1, right? Mu0 is 1. Because mu0, what is mu0? Mu0 just equal x0. So x0 is just 1. So average of 1 is just 1, right? Okay, but anyway, we just denote this as mu0, mu1, mu2. Okay. So from this, we can define this function. We can define, let's say, mu0 so plus mu1. So we use t. Okay, x so doesn't matter. So we just use t, mu1t, because for landing variable we always use x, right? X. So maybe so in avoid those confusion, so we use t. Mu1t then plus mu2t square. Okay, but here mu2t square we need divide by 2 factorial. So we just say 2 factorial. So and here, so this is just we say mu3. So 3 factorial t3 like this. So in general we say so mu k, so k factorial tk. Okay, so this function we denote this as m, this function from this landing variable x and this variable t. So okay, so we call this function as moment generating function. Moment generating function. Of landing variable x. Okay, so we call this a moment generating function because from this function we can generate all its moment. So let's say, so we have this. What is mu0? What is this moment mu0? Mu0 is just equal, we just let x, no, I'm sorry, let t equal 0, right? And what is mu1? Mu1 just the first derivative. Then let this t to be 0. So mu2 is second derivative. So we don't need to divide by, so here we put 2 factorial. So in general we say mu k is just k's derivative. Then we let t equal 0. So from this function we can generalize those all moments for x. Okay, so this is such a function is a moment generating function. Okay, so what is mu1, mu2? What is mu k? So we say mu k is this xk, right? So what is xk? This equal, according to definitions, xk's power. Then probability, or we use in continuous situation, this is a density function fx, so dx. So x changing from like, so x is just we just check all x's. So we put that negative infinity to positive infinity, means all x's. Okay, so this is mu k. So this fx density function or probability function in discrete situation probability, so in continuous situations density function. Okay, then we just plug it in here. Let's say, so moment generating function we can use a summation. Okay, moment generating function we use this summation notation. We say moment generating function equal this summation. K could be from 0 to infinity. So this is just a mu k over k factorial, then tk, right? This is Marmite generating function. Then we just put mu k as this here, k factorial. Okay, so tk, so mu k is this integration from negative infinity to positive infinity. So xk fk, no, fx, yeah, dx. So here the integration is about x, not about t. So here we can say t is constant for this integration. So we can put this inside of this integration. Okay, so we can change this negative infinity to positive infinity. So become this tk xk k factorial fx dx. And we can put this summation to the into the integration. So we can say this equal so negative infinity to positive infinity. This is summation, right? So k equals 0 to infinity. So tk xk k factorial. Okay, say fx dx. So here for summation, we just focus on summation on k. This fx, x is constant. So let's say we can put so we can do this addition summation first. Right? So then what is this? What is this summation? So we know this is just z. So let's review what is x. Let's say what is x. X, we say x just equal 1 plus x plus plus x squared over 2 factorial plus x3 factorial. So in general, x is here xk k factorial. So this is x. So we know the inside just tx, right? Okay, so we say this summation is just tx. So we say this equal negative infinity to positive infinity. This is tx fx dx. Right? Okay. So we say the Marmite generator function is this. And saying this is the fx probability multiply this. So what is this? This actually this just equal expectation or tx. So here x, uppercase x, random variable. Then t is fixed. Okay. So for example, let's say like we have this. What is this? negative infinity to positive infinity. This function, like let's say gx multiply fx, so fx is density function dx. What is this? This is just equal e gx, right? Okay, like let's say if gx equal x squared, like for example, like this, if this is x squared, then density function fx dx. What is this? This is just equal e x squared, right? Or average for those x squared. Okay, so we can say the moment generated function. So we also can define. We say this is this function. Those things are moment generating function. Like we say, we also can define this. We say define so e tx is moment generating function. We denote this as a moment. M stands for moment. For landing variables x, so moment generating function t. Okay, so we can say like how can we show this that two variable? So we can answer the questions. Two variable, how can we prove? How to prove? These two variables are the same. Two landing variable. Two landing variable are equal. So we here equal meanings we cannot say equal. We say identical. So we cannot say equal. How to prove two landing variable are the same or identical? So we can answer is we just can show like moment generating function for x and moment generating function for y the same. If the moment generating function are the same, then we can say x and y, these two variables, are equal, or equal is not so precise, we say identical. So why we cannot say equal? So let's say like we say x 0.1, a probability, let's say 0.5, 0.5, we say x is this, y is also like this, right? 0.5, 0.5. So we can say x and y same, x equal y. So that distribution is the same. But we cannot say this because x, y, what is x can be 0, so sometimes x is 0, y is 1, so x not equal y, right? So we cannot say x equal y. We just say x and y follow the same distribution or identical. Okay. So now, so we can let's say the proof this thing follow normal. Then we just say like basic ideas. We wanted to prove the moment generation function for t will equal or close to a moment generating function for x. So this x is normal. Follow some normal distribution. Okay, like x follow, I think NP like follow some normal, right? Sigma. Okay, so this is what we want to prove. Okay. Okay. So, so at first maybe we know the basic idea. We want to prove their moment function are same or close. Okay, so here in order to prove, so we need at first simplify. We just simplify a little bit. Like for normal distribution, we have too many more normal distributions, so we just consider simplest case standard normal. We wanted to change general normal to standard normal, right? So here we want to first one we say we put part A. So in order to prove this, at first we simplify. We just do some simplification or simplify. Simplify first. So make things easy. Okay. So let's say the result we want to prove is this. Like the idea of the result we want to prove this. Those x, each xi follow some distribution. So we don't care which distribution. Like normal, not normal doesn't matter. Just follow some distribution. But for any distribution, they have average, mean, mu, and sigma, right? Mean have like for any population, have the average for all and changement among those people, right? Among those things, so we have mu and sigma or sigma square. So here sigma squared values. Okay, so the result is we say the central limit theorems. Let's say the t. So t's total result is x1 plus x2 plus xn. So the t. So for t says mu t. Let's say mu t or et equal just equal n mu. So x1 is mu, x2 is mu. So those xi, we also say x1, x2. Those things are from the same distribution. Or we cannot say x1, x2 equal, but they are identically distributed from the same distribution. Okay. So mean is this, we just add them up, and variance also just add them up. We say variance of t equal, so first one sigma square, so n sigma square. Okay, so the result is there's t over, we wanted to prove of central limit theorem says there's t will close to this normal. So mean is n mu and variance n sigma square. But for normal distribution, we usually focus on standard deviation. Right? So we say t follow this normal. So we put for standard normal. So let's say, so we have this minus mu divided by sigma. So we have this. We say so t minus mu divided by this will close to standard normal, right? So it becomes standard normal. Okay, so we need to prove t minus n mu divided by this follow standard normal. So what is t? So t is x1 plus x2 plus xn. So now we can simplify this as like t minus np n mu. I'm sorry. So we can say this as t is just as I say x1 minus p minus mu. And so we just let's say divide by sigma. Let's say divide by sigma. So or divided by radical a sigma. So this equals this plus, let's say the numerator is just x2 minus mu plus xn minus mu. So each one divided by radical n sigma. Radical n sigma, like this. Radical n sigma. So we just wanted to prove those things will close to a normal distribution, and so we write this as equal. We can take a radical n. So this we can say this is just we just say this is y1 plus y2 plus yn. Okay, so what is y1, y2? So y1 is equal x1 minus mu divided by sigma, right? So y, like in general, y I is just xi minus mu divided by sigma. Okay, so so we say x1 is also xi means mu. So minus mu, then mean becomes 0. So standard deviation sigma, so divided by sigma, the standard deviation becomes 1. So we can say those yi follow some distribution with mean is 0, right? Standard deviation is 1, right? So the problem becomes just like that. We have those things like y1, y2 plus yn. Those things divided by radical n or multiply 1 over. These things will close to standard normal. Okay, so what we wanted to prove is this. We say like radical n. Okay, so y1 plus y2, those y plus yn will close to standard normal. Okay. Okay, so we simplify for this, right? So then we wanted to prove this. So how can we prove those variables, like this landing variable and a normal standard normal variable are the same? So we need to check. Let's say. So now we need to check their moment generation, right? Moment generating function, we also can write as a moment generating function, MGF. Okay, so what is MGF for? Is standard normal distribution? And then what is the moment generating function for y1 plus y2 plus yn? So for that, so check their moment generating functions at first. Let's check. Okay, so at first let's say, so what is standard normal? Let's say like suppose x follows standard normal. So what is this? So we need to find this. What is its moment generating function? Okay, so moment generating function according to definition is this, right? Moment generating function is negative infinity to positive infinity e t x f x dx. Okay, so then what is so we also have a question. What is density function? What is fx? What is fx? What is the density function of standard normal? Or what is the density function for normal distribution? So in general, we have this. We say for normal distribution, for normal distribution, density function is function of fx is thus. Let's say for normal distribution, the graph we know, the graph just like that, right? Okay, so from the center, both side goes down. So let's say in mathematics, which kind of question, suppose here is 0, accent is 0. What kind of question the graph just like that? We say this function, those functions just simply the function is thus e negative x squared. Like so, let's say negative x squared goes to infinity. Negative, so negative is the negative square, not is negative part 0, right? So this function is negative x squared, graph like that. So normal distribution density function just like that. But here we cannot guarantee that the total probability is 1, right? So here we need some coefficients make sure those total probability is 1. Okay, and so in general we have this, and x can be like we can put some coefficients, right? Like x squared over some numbers. So in general we say if we have this result, if x follows this generally normal, we just put generally normal mu and sigma. Then this density function, the density function of this landing variable f(x) is thus equal, we have this, let it equal 2 pi sigma. So e negative, so here x minus mu square over 2 sigma square. There's density functions like this. Okay, so then we also have this question: where, how can you get this? How can you derive this density function, right? Okay, so the question, let's say we also have this question: how to says, okay, this density function. Okay, say how to derive this density function, and we also have this question. Then from the if density function is this, then how to find a moment function? Find moment generating function for those normal. Okay, so we leave those things to next lecture. Okay. Okay.